Hello, everyone. Thanks for coming to this Amy AI seminar. And the presenter today is Yuqiao, who is my PhD student right now. He started his master 2 years ago with me and did some research on natural language processing. In particular, his research is in modeling the uncertainty in text generation. And his master thesis was about having some EM algorithms for multimodal text generation and published an ICLR paper. For today's talk, it's going to be f-Divergence minimization for sequential knowledge distillation. So without further ado, let's get started with our pizzas.
And the talk.
Sure. Hi, everyone. Thank you so much for attending this talk. Today, the topic is f-Divergence minimization for sequential knowledge distillation, which is a joint work with Chao Li from McGill University. When you
Speak louder.
Sure. When you do from the University of Hong Kong, and of course my supervisor Lily Mo. So first, I'd like to introduce language modeling. So language modeling in a nutshell is just the idea of predicting the probability of a text. So you give me a sentence, the language model is supposed to predict a probability for that particular sentence. And this kind of models have a lot of application, including auto completion, machine translation, and let's say dialogue as well. For example, with the recently released ChatGPT model. And auto completion is perhaps one of the most direct application of language modeling. And again, this is a very like canonical example. Basically, if you type something in Google, you say, what is a language? And then Google tries to complete the sentence. What is a language model? What is a language barrier? What is a language correspondence? Basically, you're kind of looking at the probability of the next word, and then you're just picking the top of the top words to complete the sentence. Traditionally, language modeling was achieved through n-gram models. So an n-gram model is basically, the idea is that you break a sequence of words into n-grams, and an n-gram is just n consecutive words. So let's say, for example, if I'm talking about unigram model, then I'm just breaking a sentence to a bag of words. So if we take a look at this sentence, this is a big data AI book. Then the unigram model says, okay, I treat this sentence as a bag of words, and each word I have a probability assigned to that, and I just multiply all the probability of each word together to compute the probability of the whole sentence. But as you can probably tell, this is kind of a very limited way of modeling text sequences, because you're not capturing the relationship or the context of these words. So I think a classic example would be work to live versus live to work. They convey very different meanings, but they all have the same words. So to address this kind of like problems with unigram modeling, the natural extension would be to what about if I choose a higher order n, so I look at not only the words, but let's say the words that are like two words together. So if we look at the bigram model, this big data AI book can be broken down into these like bigrams. This is big data, and data AI. And in this way, we're able to model more context just because we're just modeling more words together. But the big problem of this kind of approach is that if we do this, the number of parameters explode. As we can see, if we look at the number of words in the English dictionary, then there's around 170K words. And if we want to model unigram models, that's 170K parameters. But if we look at the bigram model, that's immediately some 30 billion parameters. And the biggest problem is also that these parameters are mostly zero, because as you can see, different word combinations, sometimes it's, if you look at a big corpus, then you don't even see a single instance. For example, if you say book AI, and then this kind of, if you multiply the words, the probability of the words together, then you get a zero probability. So this kind of model really requires a smoothing techniques to make it work. So this is where neural language models really helps with this language modeling. So instead of, let's say, modeling unigram, bigram, trigrams, and using some smoothing techniques, the main idea of neural language models is that you use a fixed number of parameters to model the dependencies of a word conditioned on all previous tokens. And it really gives you the bang of the buck, because now you're fully utilizing these fixed number of parameters, and you don't rely on like smoothing techniques. And as we can see here, let's say if I have a sentence y1 up to y key, where y1 is just a word, then you can model this probability, break it down auto-regressively, that is word by word. So you model the probability of each word conditioned on all the previous tokens. And if we look at the diagram, this is how it works. So we have a neural network. It could be an RNN or a transformer model. Let's say you have a few, a sequence already. I saw something. You put that as an input to the neural network, and the neural network predicts a probability over the entire vocabulary size. And you can basically take the argmax, for example, and you can see that, okay, the most likely next word is cat. And you can put that as an input to the neural network model, and then you can continue to generate a full sentence. What is interesting about these models is that these models perform really well as you increase the size of the language model, which is surprising, because usually you would expect a model to overfit to the training data, but that's not actually happening with large language models. So a general trend is that what we're seeing is, if I make the language model larger and larger, then the performance is better and better. So, in the industry, people just train larger and larger models, and we can see this exponential growth in large language models. But this actually brings us a big challenge, that these models aren't exactly accessible to most users or to individual researchers, because we can't fit these large models into, let's say, a single GPU. And in addition, training or inference on these large models are very slow. So this raises a natural question that, do we really need this many parameters to achieve good performance? And knowledge distillation is kind of asking this kind of framework. It is the framework that asks this question. And the idea is that if we have this large language model that's been trained so well and can perform so well, can we actually use it as a teacher model to train a much smaller network to allow the smaller student model to also perform really well? Now, why do we care about knowledge distillation, and why do we, let's say, just directly train a smaller model instead of like having a teacher model and student model, all this, knowledge distillation framework? And what we can see is that student model, of course, you can directly learn the student from the data set, but empirically we find that this is not, the student model does not perform well. But if you actually have a teacher model to teach the student, it can perform much, much better. And this can be illustrated by this MNIST dataset example. So if I directly learn from the dataset, I have an input image 3, and I know the label is 3. And in this way, I can learn, okay, this is a 3. But if I'm actually working with knowledge distillation, I'm learning from the student. I'm learning from the teacher. Then the teacher model not only tells me, oh, it's 90% 3, 90% similar to 3. I can also know, well, this 3 is also kind of similar to let's say a 6, or it's kind of similar to an 8, but it's very different from, let's say, for example, a 1. So you get more information from, than just training from the hard label. So this is why, in general, knowledge distillation works. But the problem of knowledge distillation. So what I just described is the classic knowledge distillation at the last layer. So the idea is that you learn from the output layer of the teacher model, and you basically minimize the KL divergence between the teacher's prediction and the student's own prediction. But this kind of approach has this problem, which is known as mode averaging. So because a student have to cover the support of the teacher model, it spreads its probability thin in an attempt to cover the teacher model's predictions. And here, the assumption is that here we can see the gray lines. The gray line is like has two modes, two peaks in the distribution, meaning that the model has in a very large capacity to fit, let's say, a distribution with two modes, where the teacher, because of its limited capacity, can only fit one mode. And this is what happens with the classic knowledge distillation approach. There are also other ways, for example, to learn from this teacher model. For example, I can also learn from the reverse KL. So KL is asymmetric, so I can switch the arguments for the KL. So instead of, let's say, KL of student versus teacher, I can also say the KL of the teacher versus the student. And this is kind of the ENGINE approach, which is to minimize a teacher-defined energy function of the students' generations. And this has the opposite problem of mode collapsing, where the student model learns to only generate sentences that are really great on the teacher's distribution, but it doesn't care about, let's say, another mode. So this kind of approach also is not ideal because it's missing a lot of high probability sentences from the teacher model. Another approach, so that was a knowledge distillation at the prediction layer. Another approach is recently people have started looking at, well, if you're only learning from the teacher's distributions or the teacher's predictions, then it might not be adequate. So another approach is what you would try to learn from intermediate layer, just hidden representations of the teacher model as well. So some exemplary work includes, let's say, patient KD, which learns, let's say, if the teacher has 12 layers and the student only have 6 layers, then you can either learn, let's say, every other layer versus the last 6 layers. So these are some variants. And there are also work focusing on this distillation, the intermediate layer knowledge from the transformer models, which has some like careful design for the attention mechanism as well. Now, the problem of existing work on knowledge distillation is that they do not consider the limited capacity of the student. So as I've just explained, we have this kind of diagram. If the teacher has the model capacity to learn a bimodal distribution and the student can only learn a unimodal distribution, then the student has this dilemma of either modeling the mode averaged distribution versus collapsing onto one of the modes. And this has not been carefully studied in existing knowledge distillation work. Our contributions, so first we propose a f-distillation framework where we treat KD as minimizing a generalized f-divergence function. So f-divergence includes a family of different divergence functions where if we look at the asymmetric divergence functions, we can immediately recover KL distillation and reverse KL distillation. And as we mentioned, these approaches have the mode averaging and the mode collapsing problems. Further, if we can further expand our vision to symmetric divergence functions, such as Jensen Shannon distillation and total variation distance. And these divergence functions are symmetric in the sense that if you switch the argument between the student model versus the teacher model, the divergence is actually still the same. So the distance between student versus teacher and teacher versus student is the same. And what we find is that these using these divergence functions for knowledge distillation gives us a much better balance between mode averaging and mode collapsing, which allows to achieve great performance. Another contribution of ours is that we also propose efficient computation of these f-divergent functions. So in general, divergence should be considered at the sequence level, but the sequence is level of divergence is very difficult to compute and intractable because you cannot iterate through all the sequences in a natural language. So we have derived some sequence level stepwise decomposition for such divergence functions so that we can compute this in a tractable manner. And in our decomposition, we can see that if we decompose KL, reverse KL, or Jensen Shannon divergence, these are exact decomposition. Whereas if we use a very similar decomposition for total variation distance, then it's going to serve as an upper bound for our minimization problem. Oh, what? Sorry, there's a bad connection happening. Oh, what? Oh, sorry. Oh, I was like, one moment, please. Yeah. Connection problems. Projector.
We need to identify where's the problem.
Oh,
No, it's not working.
yeah, no, it's not.
Oh,
here
yeah.
it's
Back
back.
again.
Oh,
Can people from Zoom still see my screen?
no.
They can.
You stop your sharing.
I stopped my sharing. Okay.
Yeah, you are stopping sharing.
Okay,
You
I'll
need to
share it
share
again. Oh, this is not the right one. Share screen here. And okay.
Okay.
So I was mentioning, sorry about the interruption. So I was mentioning that our approach will, although symmetric knowledge distillation, we find that they work better. They require sampling from both the teacher and the student. So this makes them inevitably slower than asymmetric method. So we further propose to apply offline sampling, where we'll only sample from the teacher model. This is intuitive because the teacher model does not, we'll only sample from the student model. This is understandable because the teacher model is never updated during our knowledge distillation. So there's no particular reason to keep sampling from the teacher model. Whereas the student is always changing. So we have to always update the student inference. We have to perform inference on the student model. Then we conducted experiments on 4 different NLP tasks to validate our approach. So we first take a look at the classic KD, which is proposed by Hinton. The idea is that you minimize the cross-entropy loss, or you minimize the KL divergence at the between the teacher prediction versus the student prediction. And this is can be factorized in this way if we because text is predicted autoregressively, so we can just directly decompose it this way. Then here some notation, we have P is a student distribution, Q is a teacher distribution, and Y is a ground truth label. As I mentioned, this is equivalent to minimizing the KL divergence, and we have to break it down word by word, just because here the language model is autoregressive. And here's a So unfortunately, what we well, not unfortunately, but some researchers come up with this sequence knowledge distillation idea, and what they argue is that KL should be minimized at the sequence level, as I explained before. And the idea is that they want to minimize the KL at the sequence level, but they can't because it's intractable. So they have an approximation for that. And what they did is that they performed beam search on the teacher model. So if we look at the word level knowledge distillation that I just explained, this is on the left-hand side of this diagram. And what we can see is that the ground truth label ECD is being used for this particular knowledge distillation. Whereas on the right-hand side of this diagram, the teacher performs a beam search and finds this sequence ACF, and then use this sequence ACF to update the student network. So if we take a look at, so yes, this is basically a textual description of what I just said. At the sequence level, we have we want to like minimize this divergence with an expectation over the sentence space, and therefore this is not so doable. So they have a beam search result, and then they just use this argmax to use this y, which is a beam search result, to approximate the sequence. Comparing the normal knowledge distillation versus SeqKD, the difference is actually very little. So if we look at knowledge distillation, the standard way, you're looking at this formula, where you're using the ground truth label. Whereas if you're using this approximate SeqKD approach, you're basically using a teacher sample instead. So this is so they're not so different, but the underlying idea is different. Now, as we can see, this knowledge distillation, this cross-entropy loss, has this property where the loss is going to be really low if the loss is going to be really negative, and so because we have a negative sign here as well, the loss is going to be shoot up to infinity if, let's say, student predicts a low probability for a teacher-generated sentence. So this is very bad, as we can see. So as a result, to minimize the loss on expectation, the cross-entropy loss basically encourages the student to predict a flat distribution. This is to avoid getting this negative infinity from this log operator. And as a result, we can see why the student tends to predict a very flat distribution, as demonstrated here with the green curve. Another approach, which kind of like tries to address this problem, is called ENGINE. And ENGINE is, the idea is basically you want to minimize an energy function defined by the teacher. So I don't want to necessarily cover all the possibility of the teacher distribution. So here, the main problem is because you are kind of evaluated based on the teacher's generation or the ground truth label, and you have to cover everything. So what if this approach is saying that, well, I don't care about what you're generating, but let's say what I care about is my student generations. If I ask the student model, which is this red block, generate a sentence, and then I evaluated this sentence based on a teacher model, and this gives me a score. So naturally, you would imagine this would solve the problem of Chao divergence and the overly smooth function. But what we expect is where we have a different problem. So as we can see, the ENGINE loss here, it looks very similar as our KL loss. And the difference here is that the samples are coming from the student model and evaluated on the teacher model. So we kind of swapped the position of the teacher and the student. And as we can see here, the problem is the student model doesn't have this, no longer has this responsibility or to cover all teachers or all teachers generation. In fact, it only needs to generate sentences that the teacher thinks is good. So as a result, if you look at the diagram, this illustrates that the teacher model is not fully covered because the student model doesn't have to. It's not part of the loss. So this gives us the other extreme problem where the student model might just fit to some like node of the teacher model and completely ignore the other half of the distribution.
How does the gradient flow into data after you do the template?
How does the gradient
So after
flow?
the approximation, you get a formula without theta, and you have nothing to optimize. Here. So after the approximation, you get a probability of the teacher of the next word of the student, given the student's predicted words, but those words are already sampled. So you don't flow the gradient into theta.
Oh, wait. No, sorry. This is here. Sorry, let me take a look.
Or they do reinforcement learning, use that as a reward signal to learn data.
No, sorry. Here, this is a little bit wrong. Sorry, this is a mistake on my presentation. So here, this is not this is a cross entropy. So you still have the probability of the token at the beginning. So you have the Q theta times log of P.
Oh,
Yeah. So that's what I meant. I was confused for a second. Yeah. So sorry about that. So there's a mistake on the slides that log of P, there's a Q before that. So the gradient is still computable.
But is that the case? I mean, if you do a Monte Carlo approximation for the expectation, you won't have the P of Q. P of Q will be the samples. If you do a Monte Carlo sampling to approximate the approximation, you won't have the probability in your function.
But this is computed word level. So the expectation is about the previously generated tokens. So it's about what you're conditioning upon. But the divergence still have the Q at the beginning.
okay. Possible. Oh, that requires further derivations. Go ahead.
So right. So now we move on to f-distill distillation. So this is our approach, and what we formulate this problem as minimizing different f-divergence functions. And as I mentioned, existing methods approximate f-distill in the sense that SeqKD is doing kind of like Chao distillation, but they're using a hard sample with beam search, and ENGINE is doing the opposite. So they're approximating reverse Chao. They're lost because it's not exactly reverse Chao, but it has the same spirit. So I'd like to first introduce f-divergence. So f-divergence, it's kind of the generalized divergence function that we're using as our knowledge distillation objective. And the general form is illustrated here. And there are a few requirements. The f function has to map from 0 to infinity. Well, has to map from 0 to infinity to a real number. And f is a convex function, and f of 1 is 0. So this is basically saying that if the p and q are the same, then the divergence must be 0. And if we look at this table here, with different setup of f, we recover a wide range of divergence functions, including the Chao divergence, reverse Chao, Jensen Shannon, and total variation distance. If we take a look at the Chao distillation first, we first look at the definition of Chao divergence, and what we see is that this is basically a formula, and as I mentioned, this expectation big Y sampled from P is not computable. Well, it's too large, so we approximated by a stepwise decomposition. This is related to our theorem saying that we can actually do this, and I'll be able to talk about this theorem a little bit further in detail later. And here basically we're breaking this sequence. This is Y, which has this many tokens, and we're breaking it word by word. And the idea is that we're calculating this summation over all the words. So the difference here is that the Chao distillation here is learning from soft labels from the teacher model instead of hard labels. And here the Y is a teacher sample, and the const is a teacher entropy, which is the teacher's entropy. It's just a constant because it's not learned. The P is not a learned doesn't have learnable parameters. And as I mentioned, SeqKD approximates our Chao distillation. If we just compare Chao distillation with our Chao distillation with SeqKD, then as we see that the only difference is that we're learning for soft labels, whereas the approximation is learning hard labels. So it's understandable that our approach is able to perform well, just as, let's say, if we recall the example I gave about MNIST digits, if you know which, the relationship between different classes or different words, then it's possible that you're going to get better performance. Another approach is reverse Chao distillation. Reverse Chao here, it's basically the difference is you swap the position of the teacher and student. And here, as you can see, the samples are now drawn from the student models, and it's computed this way. And we have a very similar decomposition, trying to address this expectation over sentence space, and we look at stepwise whatever this reverse Chao distillation is. And here, what we can see is that here we have a student entropy term. The student entropy term cannot be just treated as a constant anymore because it contains learnable parameters. And the second term is the engine loss. So this is where I missed previously. There's a q theta at the beginning here. And as we can see, the y prime here are samples from the student model. If we take a look at Chao versus reverse Chao distillation, we still have the same problem. So although the difference here that we're doing here is that we're using learning from soft labels, but it's not like we're actually solving the problem of mode averaging versus mode collapsing, because we still have the same problem because we're just minimizing Chao and reverse Chao. So this is where we started investigating symmetric distillation methods. And if we take a look at asymmetric methods, Chao and reverse Chao, they're asymmetric because if you swap the arguments P and Q, then the divergence is actually different. So this is why we call them asymmetric. And as we see, they're prone to severe mode averaging or collapsing problems. On the other hand, if we check symmetric distillation methods, we have Jensen Shannon distillation, total variation distance distillation, and what we find is that these methods give a much better balance between these two extremes. And this can be demonstrated basically here with Jensen Shannon distillation. This is a definition, and as you can see, it's kind of like what you're doing is you're like using part of Chao and part of reverse Chao, but the difference here is that the divergence computed from M, which is the average between P and Q. And similarly, we have to break this kind of expectation of over the sentence space and decompose it stepwise, and we get this kind of formula. So this is the Jensen Shannon divergence function, and how we use Jensen Shannon distillation. Another approach is total variation distance distillation. So this is different from Jensen Shannon, and as we can see here, we're basically finding the difference between Q and absolute difference between the teacher and the student model. And this is apparently obvious. Well, it's apparent that this is symmetric because it's Q minus P, P minus Q, because you have the absolute sign, it's going to be symmetric. Now, this is a little bit different because we actually cannot decompose. If we decompose this approach, this TVD objective stepwise, it's different because the resulting decomposition is actually not the exact decomposition. It's actually just an upper bound. So that's why here we have an upper bound, and we're basically minimizing this upper bound instead for TVD distillation. And this is the final result that we have. Now, I want to dig a little bit deeper into stepwise decomposition. So as I mentioned, Chao, reverse Chao, and Jensen Shannon, for these approaches, we have exact decomposition. So what we're really doing here is, if we look at the first line, we have this entire expectation of the whole sentence for both of these terms. And what we're trying to break it up is where we're trying to say, okay, we have a summation sequence from the beginning of the first token up to the last token, but the expectation is only taken with respect, to the context. So we have the prefix y of 1, 2, t minus 1. So the prefix is what we're sampling from the model, but the expectation here over the actual token at each step size, we compute this. This is why it's a soft update, because we're not approximating this summation with a single sample, whereas we're actually summing over the vocabulary. And the idea here is that the expectation, although over the sentence is intractable, we can actually compute this expectation over a vocabulary, which is usually 30K, 40K. It's actually doable. So this is what I meant. So here we would take a Monte Carlo sample of a sentence as the prefix, and then the expectation is taken over the vocabulary size. On the other hand, if we look at total variation distance, I mentioned it's an upper bound, and this can be demonstrated here. So we're doing the similar kind of decomposition, and the trick here is that this is no longer. I mean, I won't show the proof here, but the idea here is that we will apply the triangular inequality to obtain this kind of like decomposition, and that's why we have a upper bound for the divergence instead. Moving on to the experiments, as I mentioned previously, we are doing 4 different NLP tasks, including data-to-text generation, summarization, machine translation, and dialogue generation. And we've picked some very standard metrics for each of these tasks. Here, Dart is our main data set, so we have a bit more. We have like 2 sets of evaluation metrics, including blue, meteor, tur. These are based on matching the string. You're kind of like just matching the different strings. But we also have some learned metrics. So bird score, mover score, bluert. These are based on these are like popular metrics that are trainable. Okay. Looking at the results, we first take a look at compare the teacher model versus a student model that's directly trained on the data set. And as we can see across all these data sets, all these like tasks, the teacher's performance is much better than the student performance if you just directly train the student on the raw data set. And this is basically what I mentioned at the beginning, why knowledge distillation is an important framework for training the student model. If we look at compare knowledge distillation and what we call a predistillation step. So this predistillation, what this predistillation means is that we have a combination of different losses. So this is just a fine-tuning loss. We have some intermediate matching loss, and we also have a word level KD. Well, not KD, but word level KL loss. So this is a predistillation loss that's used for all this predistilled model is used on all the remaining of the methods, serving as a baseline. The idea here is that because our approach sometimes involves inference on the student model, we want to make sure that the student model is actually not degenerated. So student model has to be trained to some extent before we sample meaningful sentences from the student model. So that's why we have this predistilled model. And as we can see already, predistillation already has a helps the model to perform better than just the directly training from the data set. Now we compare SeqKD versus KL. As I mentioned, SeqKD is using a hard sample to approximate the actual expectation, whereas our KL is learning from stepwise soft labels. And as we can see here, indeed, learning from soft labels gives us a better performance than using hard labels. And this kind of phenomenon is also true for reverse KL versus engine. So we have the same conclusion that using hard label is indeed worse than using soft labels. Moving on to our symmetric methods, including Jensen Shannon divergence distillation and total variation distance distillation. Because these methods are symmetric, they are not so prone to the mode collapsing or mode averaging problem. And as we can see, this is also demonstrated by a good performance as they take the best performance. These 2 methods achieve the best performance on pretty much all 4 of these tasks. further, we truly wanted to understand whether our mode coverage versus mode averaging versus mode collapsing hypothesis is truly correct. So we have a few more experiments to analyze that. So our idea is that firstly, this mode collapsing versus mode averaging phenomenon is very much related to the diversity of it, or the task itself. So if the task itself is very diverse, then you can imagine that's like a multimodal distribution with many modes. And then in that case, it's going to play a much bigger role for the different kind of approaches, KL versus reverse KL. Whereas if you have a very, let's say, grounded task, let's say, for example, machine translation, your learned prediction your target distribution might just be a unimodal distribution, where these kind of things, KL, reverse KL might not have as much of a impact on the learning. So we use teacher dist as a dist to serve as a measure of the diversity of the task. And the idea is that if the task is much more diverse, then it has like more of a multimodal. The teacher distribution is more multimodal. And in addition, we have these two losses, which is called the likelihood loss and the coverage loss. So the likelihood loss is that you use the teacher's model to evaluate the student samples, whereas the coverage loss is you use the student model to evaluate teachers' generations. So if we take a look at the coverage loss, if the student is trying to cover the teacher, if this tells you how well the student can cover the student, and this shows that, well, if you have a high coverage, that means whatever the student has learned a good distribution that kind of like mode averages. And whereas if we look at the likelihood loss, then we're looking at the teacher's perspective. So I'll show examples in the next slide. So well, from the literature, we know that dialogue has this severe one-to-many phenomenon where, let's say I give you a dialogue context, you have multiple ways or plausible ways to respond. And in this sense, we can see that it actually has the highest teacher dist score. This makes sense because dialogue is not really grounded so well. So let's say if I compare with machine translation, if I give you a source context, the input text, then you have to translate that input text. But on the other hand, if I'm looking at dialogue generation, I ask you, what did you do last weekend? Then there are so many different ways you can respond. So that's why we see this as a one-to-many task.
What did you do last week?
Oh, well, we had something. Okay, yeah. Last weekend was fun. Yeah. Anyways, yeah. So here we can see that KL indeed have low coverage, which is indicated by this highlight, which shows it's. Oh, I did this wrong again. This is a mistake. But yeah, so if we look at the performance of KL and reverse KL, we can see that indeed reverse KL performs much better than KL distillation on the dialogue task, because you can see that the student model doesn't have enough capacity to capture all the different ways to respond. So if you just cover one way to respond, then that's already good. And this is also shown in the likelihood loss and coverage loss. So we can see here the likelihood loss is really low, meaning that it's very likely the reverse KL is generating likely sentences, which is likely is judged by the teacher. The teacher thinks this reverse KL is generating good sentences. On the other hand, reverse KL is not covering the teacher's generation. So this kind of affirms and confirms our idea, our hypothesis about one-to-many, this limited capacity kind of diagram. Another analysis we did is to try to study, does our approach work with differently sized models? And indeed, as we can see here, we tried different configurations, including the different number of layers for the student model. As we can see here, Jensen Shannon and total variation distance distillation consistently performed much better. Well, then SeqKD, reverse KL, and KL across different model sizes. So this shows that our approach is generalizable to different sized students. We also have analysis on if our offline sampling is actually effective. So at the beginning of the talk, I briefly mentioned that the symmetric methods require sampling from both the teacher and student model. And we believe that this inference from the teacher model is unnecessary. We can just, let's say, perform inference once at the before training and then use those samples during training without making inference every time. And here we can see that this indeed doesn't affect the performance much, but it gives us a much faster speed up. So in fact, the speed is more than doubled. And the reason why it's more than doubled, even though I'm somehow I'm reducing half of the computation, is that sample from the teacher model is much more expensive because the teacher model is just much more larger. We also have case studies to try to see is it true, does KL and RKL truly have the problems, and does do Jensen Shannon and total variation distance can improve that? And then the answer is yes. If we take a look at KL and reverse KL, so the first task we take a look is DART, which is data to text generation. So if we look at the input is triplets, we have the number of the train, the destination is Mumbai, and the origin is Chennai, and the number here, the name of this number is Mumbai Mail. And the reference, well, is this, the name of the train is Mumbai Mail, has origin and destination of Chennai to Mumbai. So this is the reference. As we can see here, KL and reverse KL, they both don't, they're incoherent. For example, if I look at the KL, the train name of the train that originates from Chennai is Mumbai. So this is completely nonsense. But if we take a look at Jensen Shannon versus total variation distance, then these sentences actually make sense. Like, for example, the Mumbai Mail train starts from Chennai to Mumbai. This is actually a good generation. We also took a look at common sense dialogue, because dialogue is quite well known for this one-to-many problem that I just mentioned. And indeed, we can see that KL generates very short and generic sentences because it's a mode averaging problem. So you're not generating some typical sentences, but you're trying to be safe and just give a very generic and short response. Reverse KL is nice because it's trying to generate a very long and detailed response, but the problem here is that it's not grammatical. Like if I try to read it, I'm going to miss my mom and dad. I'm going to miss my dad and the people I have to do a lot of things. It doesn't really make too much sense. But if we take a look at Jensen Shannon and to the variation distance, then it's really detailed and it's fluent. For example, I'm finally done packaging my dorm. I can't wait to start my first year of college. Moving on to the conclusion. So in this work, we have proposed f-distill that generalizes existing approaches. We have asymmetric methods that covers SeqKD and ENGINE based on KL divergence and reverse KL divergence. We have also explored symmetric distillation methods such as Jensen Shannon and total variation distance distillation. We derived we have stepwise decomposition for these divergence functions, where we have shown that KL, reverse KL, and Jensen Shannon, these divergences can be decomposed exactly, whereas total variation distance can be decomposed as an upper bound. We have ran we have tried our experiment, our approach on 4 different NLP tasks, and we have analyzed the likelihood, the coverage. We have tried to study whether student size play a role. We also studied the efficiency and have shown some case study. As for future work, we have intermediate layer f-distill. So what we have done right now is working on the prediction layer of the student model. So it's inevitably bad in the sense that it's not inevitably bad, but like if the model is getting deeper and deeper, you can see that the loss from the last layer can have a harder and harder time propagating to the middle layers of the student network. And this is also So one approach is that we can think about is of how do we apply this kind of f-distill framework to middle layers of a student model. And another approach that we're thinking about is importance sampling for f-distill distillation. So because we're trying to avoid the sample from the student model as well. So right now, we still have the sample from the student models, but what if we can completely remove this sampling procedure from student model as well and use some importance sampling ratio to correct the loss for directly using offline teacher samples. That will make our approach even more efficient. All right, thank you very much. If you have any questions, I can try to answer that right now.
Okay, so now we're done. Now it's over.
Oh yes, I'm done.
Okay, any questions?
Hi, from Concentric Plantation. I have a question regarding the performance when compared offline and online distillation.
Yeah.
So can you provide us with some more explanation why you think offline distillation performs better? Empirically show that offline performs better than online.
Yeah. Give me a second to go to the slide.
It's almost an end of.
Yeah. I moved way too far. So yeah, so the question was, how do I compare online and offline? Here, I can even show why the offline performance is slightly better, right? So I wouldn't say the performance is slightly better. It's just a little bit better, and it might just come from random noise of training the neural network. This is not a significant improvement, as we can see. The performance is pretty much similar, so I don't think the performance will be much higher, let's say, using offline approach. This might just be noise.
That was when I was thinking this phenomenon. I suppose the noise experiments experiment results can be one explanation. Another reason I'm thinking is because we performing online distillation, you have this mechanism that generates samples from the student model. Because of the noise of the sampling, sample sequence, we may sample a few different samples, generations for the student model to learn every time. And that causes like slightly generated results.
Right.
In the end, we really want one-to-one rather than one-to-many training. Without one, but if your model is able to capture multiple modes, then maybe the one-to-many sampling of teacher model is better. I don't know if I make my question clear.
So you're saying if,
Because
let's say, so you're saying that like online approach could still be much better. Let's say if the teacher is learning a diverse kind of ways of respond, and then you can use like sampling to perform better because you can sample different kind of responses and the student can learn from. I think so. Yeah. So in general, I still think the online methods should, well, it doesn't have to be online. You can also just sample more. We didn't try to sample more in our case, but if you sample more, I expect the performance to go up as well, because you can just learn from more data samples from the teacher model. But there's also a problem. If you sample more, then you're giving the student more problems in the sense that you have to learn more. So like if the student capacity it's a kind of a trade-off. If you give the student too much work, then it also might not work so well, I think.
And I feel like it can be good experiments for testing all the kind of losses. With some loss, when you have this multiple reference, they may perform worse, and your method may become better when there are multiple references.
This means don't talk to your supervisor in your program. Ask them to write down their suggestions before starting your program. Then down to offline.
Keep asking, get different guidance every time. Then
yes.
But it depends on students, right? Students
but the performance here is really marginal. Every can try it for a program. Great. Thanks for the.
Thank you. I see someone there's a chat. Oh, Zidring is asking, is predistillation an essential step for your method? So that's a great question, because We believe it is because as I mentioned, we're actually relying on student samples. So if the student is just generating completely nonsense at the beginning of training, then it might be very bad. But we actually haven't really tried reverse KL without predistillation to see if it's actually really bad. So I think that's another experiment that I can make sure to include to make a more compelling statement. Thank you, Zijun.
Any questions from the audience in the room and also online? So I have a question. You mentioned the student model capacity is limited. But what if you have the same capacity? Let's say you just distill the teacher to the same architecture. Does your approach work well? Or
yeah, so the question was, what happens if I'm trying to distill teacher and student models that are of the same size? I think this is a known technique called born again networks. So the idea is that you still perform knowledge distillation, but your goal is not to reduce the number of parameters of the teacher or the student model, but you're hoping to generalize better from you just continue to distill from yourself. And I think there are literature saying that it's a good thing. It improves performance, and it's mostly, I think, done with classification literature. I have actually tried doing this kind of distillation for the generation task just here, but I haven't seen a good performance improvement. So I think there's still a lot of questions about whether why it didn't work in my case. And yeah, I think that's still.
Sorry, I just want to put a few words on this, comment on this, because there's work on using autographs transformer to deploy autograph transformer.
Born again networks.
I think the picture on the board.
Okay.
That's on sequence training.
Yeah.
In their paper shows marginal improvements when you distill again and again.
Mm-hmm. Marginal improvements when you distill again and again.
It's still noticeable.
Noticeable. Okay. Yeah.
What is the ratio of the size of the student or the teacher?
The ratio
of the size of parameters.
Oh, yes. So I didn't show the number of parameters of the teacher and student here, but roughly the student is a third of the teacher. So it's like it has a third of the parameters in general, but we have some more detailed numbers.
So it may be possible to have a few students to capture all the teacher knowledge with much less parameters than the teacher and solution, right?
So we did try even smaller. So when I say it's a third of the teacher's parameters, I meant with three layers. So we tried reducing it more. As you can see, the performance is not like super low. It's still somewhat in the same range. So you can see that indeed, like, knowledge distillation is helping a lot in the sense that, sure, I'm like the number of parameters is much lower, but it's still working decently well, I think.
So how can we adapt this loss functions in a way that if we have more than one student, encourage them to capture different models?
Mm-hmm. Yeah, I think that would be a good direction to go as well. So like the question is, what happens if there are multiple students trying to learn from the same teacher, and maybe you can ask the different students to learn different parts of the teacher model. I think that's a interesting research question, and somehow relates to my experience in my master's work. So in my master's, as Lily introduced, I did a mixture modeling for diverse text generation. And the idea there was that we have different decoders. So in text generation, you usually have an encoder and decoder model, and I have a mixture of these models trying to capture the different aspects of the dialogue generation task. So I think that's also an interesting question, like how should we use multiple teachers to learn the same model, to learn from a same teacher model, and then how to have them like learn different aspects of the teacher model. I think that's
Okay, great. I guess due to the time limit, I think the session is over, but you are still free to ask questions.
Yeah.
But just the session is over, and then next week I'll get for presenting and answer questions.
Yeah. So yeah, thank you everyone for attending remotely as well.